In my Structural Engineering Made Simple series, today I talk about design of bearing walls. This is part 1 of a two-part series and focuses on brick and concrete masonry unit walls. Please take a moment and read the disclaimer at the bottom of this slide before we continue. Bearing walls made up of masonry or concrete provide support to roofs and floors. They are generally used as backup walls. However, in some buildings they may also act as a facade. In most modern applications, these walls are reinforced, as explained later. This is part 1 of a two-part lesson on design of bearing walls. It focuses on walls made up of bricks or concrete masonry units, CMUs as we call them. For concrete wall design, please watch lesson 14 of my series on structural engineering made simple. This lesson primarily covers walls that are under the application of the floor and roof loads, identification of the types and sources of damage, and common repair methods that can be prescribed as part of the building envelope rehabilitation. These are the references used in the preparation of this video. Especially, reference number 2 highlighted in red is the one mainly used in this video. The loads on bearing walls generally consist of dead, live, and snow loads transferred from the roof and floors. These loads will usually result in an axial load applied on the cross-section of the wall. Lateral in-plane loads from wind and seismic effects. These loads are often prevalent when the wall is also acting as a shear wall. And out-of-plane forces. These are present when a lateral force acts perpendicular to the wall plane or when the axial compression load on the cross-section is eccentric. An example of a lateral force applied perpendicular to the wall plane is when a wall is subject to soil pressure, such as for example in a basement wall as shown in this figure. This figure, taken from ACI 2014, shows all possible loads on a bearing wall. You see in-plane shear, axial load, in-plane moment, out-of-plane moment, and the self-weight of the wall. The vertical direction is along the height of the wall, as specified in ACI 2014, and the horizontal direction is along the length of the wall. In most low-rise applications, the loads are primarily the axial compression from floor and roof and self-weight of the wall. Lateral in-plane shear may also be present because the wall will need to resist the shear that is transferred to the roof or floor from the effect of wind or earthquake forces. This figure shows the floor attachment to a masonry wall. You will notice that the floor joists provide the support for the concrete slab, and the system is resting on what we call a reinforced concrete bound beam. The following figures show how the wind load in the east-west direction is transferred to the roof of a single-story building. See the figure to the right, and must be resisted by the south and north walls along the wind direction. If you take a look at the lower left figure, that one shows a roof framing diagram that transfers the force to the walls. You look at the upper left figure, the force from the wind is transmitted to the north and south wall. Also, again, as shown in this figure, the floor system is made up of steel joists that are supported by a reinforced concrete bound beam. Bound beams are also in the form of special shaped masonry blocks filled with concrete like grout and reinforced with longitudinal bars, as explained later. Often the joists are secured to the bound beam with anchors to prevent movement. Other alternate floor system options may be A. One that is made up of timber sections attached to the wall through elements called hangers. Hangers are installed on a timber beam called the ledger beam, which is secured to the wall. In the figure to the lower right, you notice the ledger beam is secured to the wall, providing a support for floor joist. B. Steel profiles such as channels and W sections along with a reinforced concrete floor slab. In new repairs, if the wall has to support timber joists, a change in design will need to be done using proper attachment via hangers, which is considered the standard of the practice. The ledger beam will also need to be replaced if needed. The figure to the right shows a ledger beam. Notice that the locations of hangers are marked on the ledger beam. The anchor bolts shown are designed for the shear force and also sometimes for a tension force transferred to them from floor joists. The figures to the left show you the hangers, and these are by a company called Simpson Strong Tie, commercially available for use. Notice that when the load is applied on one side, a bending moment develops. As shown in this figure, the moment developed is M equal to R multiplied by E. E is the eccentricity of the applied load, R is the reaction from joists. The question is, how significant is the effect of this moment on the wall design? If the center of the resultant of axial load is within the middle one-third of the cross-section, there will not be any tension developed in the wall. In this situation, we can ignore the bending moment. This means that the eccentricity for the resultant, let's call it E prime, has to be less than h over 6, where h is the thickness of the wall. This can very easily be shown by employing the equation used for the axial tension or compression stress on the wall cross-section. Let's look at the figure given. The cross-section of a wall given. The cross-section is divided into 3 segments of h over 3 each, where h is the wall thickness. The eccentricity of the load is E, and the middle third of the cross-section is shaded. When eccentricity is smaller than h over 6, that means the location of the load application is within the middle third. There will not be any tension developed in the cross-section. Also notice that we have taken the effective length of the wall as LE. For a wall section with a thickness h and effective length LE, the stress on the cross-section is from the following equation. The stress F is equal to P divided by A plus or minus P divided by SX, where A is the cross-sectional area of the wall over the effective length. In other words, A is equal to LE times H, and Sx is a section modulus of the wall cross-section, which is the moment of inertia divided by h over 2, and the moment of inertia is LEH cubed divided by 12. Therefore, if we plug those into the equation, we come up with the final equation for a stress, which is P divided by LE times H, 1 plus or minus 6E divided by H. The positive sign in this equation indicates compression stress, while the negative sign means tension. Therefore, if the term 1 plus or minus 6E divided by H becomes negative, there will be a tension stress developed in the section. Therefore, to avoid any tension stress in the section, the eccentricity E will need to be less than h over 6. We show again the figure. This implies that the point of application of the force P has to be within the middle one-third of the cross-section. Let's examine this through an example. In a one-story building, an 8-inch masonry wall supports the load from a roof. The total factored load transferred from the roof to 1 foot of the length of the wall is 520 pounds per foot. Now please notice that this is the factored load. Whatever load is involved in the roof, which is generally dead load and snow load, these loads have been multiplied by the respective load factors. For example, the dead load factor is equal to 1.2. The height of the wall is 18 feet. A ledger beam of 2 by 12 inches is used to attach the floor joist to the wall. Notice that the reinforced CMU masonry has a density of about 125 pounds per cubic foot. We want to find out whether there will be any tension developed in the cross section. Based on the above information and knowing that the 2 by 12 beam has a width of 1.5 inches, the eccentricity of the load from the roof E is equal to 8 inches divided by 2. Remember, 8 is the thickness of the wall, plus 1/2 an inch, which is the effective thickness of the ledger beam. So the eccentricity of the load is 5.5 inches. However, we need to incorporate the self-weight of the wall into the picture and recalculate an eccentricity. That eccentricity we call it E prime. The external moment is RU multiplied by E, which is 520 multiplied by 5.5 inches is 2,860 inch-pounds. The self-weight of the wall for 1 foot of the length, considering 1.2 as a load factor, is 1.2 times 18 feet, which is height of the wall, multiplied by thickness of the wall, which is 18 divided by 12, multiplied by density of the wall, which is 125. The answer is 1800. So we add this to the applied load, 1800 plus 520. The total axial load right now is 2320. So our modified eccentricity, the one we show it with E prime, is 2860 divided by 2320, which is 1.23 inches. Certainly this is smaller than the thickness divided by 6, which is 1.33, which means there is no tension developed in the cross-section of the wall. Wall foundations. A bearing wall rests on a continuous foundation. The foundation needs to be designed properly for its size and reinforcement based on the soil bearing capacity and the pressure that is applied on the supporting soil. This pressure is because of the total load transferred from the wall, including the walls and foundation self-weight. If the foundation is buried at some depth from the ground surface, which is generally the case, especially in cold regions, the weight of the soil, which is called surcharge, must also be considered in the design of the foundation. Some bearing walls, especially those made up of all concrete, may also be subject to a lateral force perpendicular to the plane because of the soil pressure. This will be, for example, in a building that is on a slope, and as such part of the wall may be buried under the ground. In situations like this, the stability of the wall and its foundation will also need to be investigated if any kind of damage such as cracks is attributed to the soil pressure. Reinforcement for brick and CMU walls. Brick masonry and CMU walls will need to be properly designed for the applied loads, especially when lateral loads are present following the design codes. The reinforcement is made up of both horizontal and vertical rebars. Furthermore, the masonry blocks are filled with concrete-like grout in about every fourth core where the vertical bars are located, and as such the bars are particularly embedded in grout, thus maintaining the bond between the steel and the masonry material. The horizontal reinforcement is usually in the form of a lattice bar and is placed in the mortar joint at every other course. This figure illustrates the schematics of vertical and horizontal reinforcement. In this figure, CMUs are used in the wall. Please notice that the bar spacing for the vertical bars is every fourth core. Also notice that they are embedded where the grout is. The horizontal bar is every other course in the form of a lattice bar, like a truss. Vertical bars are usually number 4 or number 5 bars at every fourth core filled with concrete-like grout. Each bar number 4 has 0.5 inches of diameter and 0.2 square inches of cross-section area. The diameter and cross-sectional areas for number 5 bars are 5/8 of an inch and 0.31 square inches respectively. A complete table of reinforcing bar sizes are provided in the next slide. Usually small size bars are used. However, in reinforced concrete walls, especially those used as shear walls in taller buildings, large size bars are very common. This is the table of reinforcing bars. The US customary bar size is shown in the first column, which runs from number 3 bars to number 18. And the equivalent metric numbering system is also shown. For example, for number 4 bars, we are talking about a nominal cross-sectional area of 0.2 square inches. Please note that the diameter for this bar, the nominal diameter, is 4/8 of an inch, which is 0.5 inches. Horizontal reinforcement. Horizontal reinforcement is often in the form of prefabricated lattice bars using gauge 9 or 10. This table summarizes data on several gauges using the American Wire Gauge AWG designation. Please note that this table doesn't show all the gauges. We have especially highlighted gauge 9 and gauge 10. You notice that, for example, gauge 9 has a diameter of 0.1144 inches, while gauge 10 has a diameter of about 0.1019 inches. Types of CMUs. There are two types of CMUs, type N and type S. Type N is used for above or below the ground. Type S is for above the ground applications only. In this figure, you see a type of CMU block. You notice that various designations are used for different parts of this block. Each CMU is about 16 inches long and about 8 inches high. The width can be 4, 6, 8, 10, or 12 inches. For 2 to 3 story buildings in normal applications, the width is usually 8 inches. Note that nominal sizes are different from actual sizes. For example, for a height of 8 inches, the actual size is 7 and 5/8 of an inch. For a length of 16 inches nominal, the actual length is 15 and 5/8 of an inch. For a width of 4, 6, 8, 10, and 12, usually the actual width is the nominal minus 3/8 of an inch. There are also terminologies used for brick and CMUs that you need to be familiar with. When we say a block course, we are talking about a horizontal layer of blocks. 3 blocks stacked on top of each other are referred to as 3 courses. When we say width, we are talking about the vertical layer of masonry. And these terminologies refer to the position of the blocks, the following: a stretcher, soldier, header, roll-lock stretcher, sailor, and roll-lock. Please notice that the shaded area represents the face of the wall. Earlier, we talked about bound beams. Here are some examples. In this figure, you'll see a bound beam which is installed at the top of a parapet wall. A parapet wall is the wall on the roof, and in this case, it's a masonry wall. You notice that the roof is made up of steel joists. This is a better detail of the area. You notice that the bound beam has a slope at the top, inward, and it has at least 4 longitudinal bars plus a tie reinforcement, which is called a transverse reinforcement. It is also secured properly to the masonry through anchor bars. Bound beams may be made up of special shaped CMUs, as we said before, reinforced longitudinally and filled with grout. Here is an example. You'll see that the reinforced masonry bound beam has a U shape, has 2 bars in it, and is filled with grout. And the detail of CMU blocks in U shape used for making bound beams are shown in here. You notice that the figures shown in the lower right, one of them has a little recess, and that is when vertical bars need to be installed, and therefore that kind of block accommodates for the passage of vertical bars. The stress conditions in brick and CMU bearing walls. In general, the stress conditions in brick and CMU load-bearing walls are in the form of cracks, displaced or damaged blocks, crushed blocks, and loss of mortars. Another factor contributing to failure in both brick and CMU bearing wall is inadequate or lack of reinforcement. Cracks in masonry load-bearing walls can be caused by such factors as temperature variations, differential foundation settlement, heavy axial compression loads, excessive in-plane shear force, and excessive out-of-plane forces, which cause bending moments. Temperature variations often result in nearly vertical cracks. This is prevalent when the wall is relatively long and there are no expansion joints provided. Expansion joints provided at about every 25 feet along the wall and 10 feet from the corner will practically eliminate this kind of cracks. A differential foundation settlement often results in diagonal cracks and in certain cases a cluster of short vertical cracks as well. Heavy in-plane shear forces, which are usually the results of wind or earthquake loads, will also result in diagonal cracks. When heavy out-of-plane forces are applied, bending moments develop. If the wall is not properly designed and reinforced for these forces, horizontal cracks may develop. Depending on the type of masonry blocks, mortar types, and grout use, cracks may run along joints or through blocks as well. Now this figure shows different types of cracks, so let's examine the cracks we talked about. The one designated by number 1 means diagonal crack. Foundation differential settlement or large in-plane shear forces are usually responsible for this kind of cracks. Horizontal cracks shown with number 2, and these are because of large out-of-plane forces mainly. Vertical cracks or short vertical cracks are mainly because of lack of expansion joints and temperature variations or large axial compression load or even foundation differential settlement. Repair methods. Small cracks of width about 1/8 of an inch and smaller can be repaired with mortar as long as the crack is stable and is not growing. If cracks are severe, the wall segment or the entire wall may have to be rebuilt with proper design and adequate reinforcement and grout. Bound beams may also need to be constructed as needed. In situations when the wall needs to be reconstructed, we must also investigate the condition of the foundation. If the foundation is in good shape, still we need to compute the total load transmitted from the foundation to the soil to make sure it is adequate with consideration for the soil bearing capacity. If the existing foundation is utilized, dowel bars will need to be embedded and secured using epoxy in the footing. These dowels will be overlapping properly with vertical steel reinforcement. If the foundation is not adequate, a new foundation will need to be designed. Displaced, crushed, and isolated cracked masonry blocks will need to be removed, area cleaned of debris, and new blocks placed with mortar applied to repair the wall. This figure shows the embedded dowel bars with epoxy in an existing footing, which is overlapped with vertical bars. The overlap follows the recommendations of the dowel bar manufacturer, and usually we are talking about at least 6 inches. Design in seismic areas. When masonry walls are subject to seismic forces, provisions for design in seismic areas will also need to be followed to ensure strength and ductility requirements. Please review these requirements in the ACI 2013 in the list of references we provided. The material entitled as Building Requirements for Masonry Structures. Thank you for watching this video.